Hi everyone, in previous lecture we have seen the synthesis of S-propane diol, and in this lecture we are going to start our next target molecule, that is the R and S-epichlorohydrin. So here it is the structure for R and S-epichlorohydrin. So basically what are the epichlorohydrins? So epichlorohydrins are nothing but the three-membered oxyrenes, or you can say the organochlorine compound and an epoxide. Okay, so here these are the structures for the epichlorohydrin. This is the structure for epichlorohydrin, that is the organochlorine and an epoxide. This is called epichlorohydrin, and the configuration for this structure is R. Why this is R? Because here if we give the priority order, then this is the chiral carbon. This bond or this oxygen make the first priority, then second one of this, third, and last one, fourth priority is below the plane hydrogen. Therefore it rotates clockwise, and the configuration for this molecule is R configuration, and for this is S, because this CH2Cl is below the plane. Therefore the configuration for this epichlorohydrin is S-epichlorohydrin, and this R and S-epichlorohydrin are nothing but the mirror images of each other, or you can say non-superimposable mirror image. Therefore these two are the enantiomers of each other. Okay, so basically what are the epichlorohydrins? The epichlorohydrin, abbreviated at the ECH, it is an organochlorine compound and an epoxide. So despite its name, it is not a halohydrin. It is a colorless liquid with a pungent garlic-like odor, moderately soluble in water but miscible with most polar organic solvents. It is a chiral molecule. Here it is a chiral carbon. Therefore, this is a chiral molecule, generally existing as a racemic mixture of right-handed and the left-handed enantiomer. These two are the enantiomers. Epichlorohydrin is a highly reactive electrophilic compound and used in the production of glycerol, plastics, epoxy glues and the resins, epoxy dilutes and elastomer. So these are some uses, or you can say the applications of these epichlorohydrins. So see the synthesis of R and S-epichlorohydrin. These are the structures for, this is the R-epichlorohydrin and this is the S-epichlorohydrin. So the epichlorohydrin is a versatile precursor in the synthesis of many organic compounds. For example, it is converted to glycidyl nitrate, an energetic binder used in the explosive and the propellant compositions. The epichlorohydrin is reacted with an alkali nitrate such as the sodium nitrate, producing glycidic nitrate and the alkali chloride. It is used as a solvent for the cellulose resins and paints, and it has found use as an insect fumigant. Polymers made from the epichlorohydrin, for example the polyamide epichlorohydrin resins, are used in the paper reinforcement and in the food industry to manufacture tea bags, coffee filters and the sauces, causing as well as with water purification. An important biochemical application of the epichlorohydrin is it is used as cross-linking agent for the production of Sephadex, size exclusion, chromatographic resin for the dextrin. So these are the applications of the epichlorohydrins. So let's see the retrosynthesis for the epichlorohydrin. So in first step, here we have a epichlorohydrin. This is the disconnection arrow. This arrow is a disconnection arrow, and here we write the FGI, that is the functional group interconversion. Means this functional group we can convert it into another one. So here we convert this into this molecule. This is the chiral carbon, and this R and this R are the different alkyl groups. In next step we converted this into this aldehyde. and after this aldehyde is get converted into D-mannitol, and finally after the D-mannitol we got D-mannose as our precursor. So for the synthesis of R and S-epichlorohydrin, our chiral precursor is D-mannose. So by using this D-mannose we can convert or we can synthesize the R and S-epichlorohydrin. So this is nothing but the retrosynthetic analysis or a retrosynthesis for the epichlorohydrin, and in examination this retrosynthesis is asked for the half mark. See the reaction here, our starting material, that is the D-mannose, and these are the reagents to make the R-epichlorohydrin. So see one by one. First D-mannose, then the first reagent is NaBH4 in presence of NaBH, in presence of MuH. This is the reducing reagent to form D-mannose or to convert the D-mannose into D-mannitol. In next step we use the acetone in presence of acid for the protection. Then this is nothing but the LTA, lead tetraacetate, to cleavage of carbon-carbon bond. Then NaBH4, TSCl in pyridine, and so on. These are the reagents which used for the preparation of R and S epichlorohydrin. So the R and S epichlorohydrin are the three-membered oxirane. This oxirane can be easily prepared from the R glyceraldehyde, and this R glyceraldehyde can be easily obtained from the D-mannitol. Means what? For the preparation of epichlorohydrin, our chiral precursor is D-mannitol, and D-mannitol is come from the D-mannose. See the synthesis of first R-epichlorohydrin. So here we have a D-mannose. This is the structure for D-mannose, and our first reagent is NaBH4, that is the sodium borohydride in presence of methanol, and it will convert into this mannitol. There is a reduction of this aldehyde group, and we got here the CH2OH. In next step there is a protection of diols. Here diol, and this diol can be protected by means of this, and we got the 1,2,5,6 diisopropyridine D-mannitol, or you can say it is a diacetonide molecule. In next step there is a lead tetraacetate. This is the oxidizing reagent to cleave this carbon-carbon bond, and we got the two molecules of protected glyceraldehyde. And in next step again we use the NaBH4 to reduce this aldehyde into this alcohol, that is the primary alcohol. And in next step there is a tosyl chloride to convert this OH into this OTS group. So here this structure we can also write as like this. In next step we use the aqueous H2SO4 for the deprotection of this diol, and we got two molecules of this OH, that is a diol. In next step this sodium methoxide is used. This is the strong base, and it can easily abstract this proton over this oxygen, and we got here the O negative, and as we know the OTS is a good leaving group, therefore this negative charge is attacked over this and OTS leaves the molecule, and we got here this epoxide. In next step we use the MScII chloride in presence of pyridine. Pyridine is a base, therefore it can easily abstract this proton, and we got the molecule as like this. After the abstraction of this proton, here it is a formation of negative charge, and it can easily attack over and the chlorine is leaving this molecule, and we got here it is a OMS. So after the formation, that means this OH group in the previous structure is converted into this OMS when this molecule is reacted with the MScII chloride in presence of pyridine. Then after we use the concentrated HCl, and here it is a chloride. This negative charge is attacked over this, and this epoxide ring is opening because here it is a 3-membered steric hindrance. Therefore this can easily open when we use the concentrated HCl. This Cl negative attacked over this, and this bond is open over this oxygen, and after the protonation, here it is a OH, and in next step there is a removal of MSOH, and we got this epoxide. So this is the R-epichlorohydrin. So this is the overall mechanism for the R-epichlorohydrin. So the D-mannitol can be protected in presence of acid under the dry condition to form the corresponding diacetonide. We starting the mechanism or the synthesis from the D-mannose. D-mannose is our precursor. Then we convert the D-mannose into the D-mannitol. Okay, and then after the D-mannitol can be protected in presence of acid, and we got the diacetonide, and this diacetonide can be converted in presence of a LTA to form the protected glyceraldehyde. So this is the main step of our synthesis. First of all, the D-mannitol, then the D-mannitol is converted into diacetonide, and this diacetonide is again protected and the cleaved when we use the LTA, and we got the protected glyceraldehyde, and this protected glyceraldehyde can be converted into alcohol in presence of NaBH4. Then after, this alcohol can be protected under the basic condition in presence of TSCl. Means here we have this OH, and this OH is converted into this this OTS molecule. This is the tosylated product, and this tosylated product can be deprotected in presence of acid, that is the aqueous acid, to form the corresponding diol. And this is an important intermediate in the synthesis of R and S-epichlorohydrin. So in first step we see the synthesis of R-epichlorohydrin. Okay, and for the synthesis of S-epichlorohydrin, it can be synthesized by using this intermediate and the reacting it with triphenyl phosphine, that is the PPH3, in presence of carbon tetrachloride, that is the CCl4, to form the corresponding chlorinated product. Means what? The intermediate step in the both R and S-epichlorohydrin is the same, but the last step for the S-epichlorohydrin is something different. Here we use the reagent triphenyl phosphine in presence of CCl4. This is the apple reaction, and we got the corresponding chlorinated product. So in first mechanism we have seen the synthesis of R-epichlorohydrin, and now we can see the synthesis of S-epichlorohydrin. So again we starting from the D-mannose. Here are some reagents to make the S-epichlorohydrin. Here we have a reagent from number 1 to number 6. These reagents are same as we seen in the R-epichlorohydrin, but the difference is only the triphenyl phosphine and CCl4 and this ethylene glycol in presence of a Na. These two reagents are different for the synthesis of S-epichlorohydrin. So see the mechanism. Here we starting from D-mannose. D-mannose is converted into D-mannitol. Then after the protection, we got the diacetonide. Then LTA, we got the protected glyceraldehyde molecule. Then reduction of this aldehyde into this primary alcohol. Then after, the tosylated product we can get after the reaction of TSCl. And then this OTS can be, Here we use the aqueous HCl for the D protection, and we got this diol again. We can write as like this. Then here we write the PPH3. This is the triphenyl phosphine and the carbon tetrachloride. It can be converts alcohol into the alkyl chloride. So here the conversion of this OH into the Cl. This is the Apple reaction. This can convert, this reagent is converts this alcohol into this alkyl chloride. And then after the reaction of ethylene glycol in presence of sodium, we got our desired product, that is the S-epichlorohydrin. So this is the overall mechanism for the synthesis of S-epichlorohydrin. I hope you understand. Thank you for watching.